Yo, what up? Welcome to Made by Ozzy. I'm Ozzy, and this is a channel where we're turning this FPGA dev kit into a crypto miner and a GPU. We've done a whole lot of stuff so far that hasn't been directly tied to either one of those things, and so we're starting the last step of the core setup here today. If you haven't been following along with the videos, you could always go get the whole repo from GitHub. I'm going to put the link in the description. You could just go sync up immediately. Everything I'm going to show in the video today is already up in public on GitHub. And what we're going to do today is we're going to build a way for us to talk to this thing from some software we write on our computer, like Python or C++. I'm going to use Python. What we're going to build for ourselves is a RS-232 communication protocol. Some people, you may have seen RS-232 called UART, U-A-R-T, Universal Asynchronous Receiver Transmitter. Or serial. That's another way to call it. I call it serial a lot. We're going to use these two things, this and this, to actually communicate, to actually get everything plugged together. My PC does not have the correct serial port to be able to support this protocol. So let's go over what these things are. This is a, let's see if I get it in the camera right here. It's a little USB to serial adapter. This is a 9-pin connector. I got this off McMaster. We'll go over what that is, but this lets me plug into my computer, and the computer will pick it up as a USB device, and then I'll be able to talk over the communication protocol on the other end using some logic in there. This guy is a level shifter. What this does is it has the same 9-pin connector that's on that adapter, and it breaks out 4 pins. These 4 here, and I soldered on these wires extra. I got these little hookup cables off of Amazon, and because they're pretty cheap. It was like $3 for like 40 of them or something. This is just a really convenient little thing to both make sure that I'm not going to burn up my FPGA by connecting external hardware to it, and also it's a convenient breakout for the wires I actually care about. Okay, so RS-232 is a pretty big topic in itself, so I'm going to have to break this video series, or this topic specifically, implementing RS-232 into a couple videos of its own. Today, our main goal is just to get all of this physically connected, computer to this, to here, and actually get some test scripts working to make sure that let's tie the inputs and outputs to LEDs on here, make sure we could see them blinking, make sure we could responds the way we think it's going to respond, and then let's also get a Python project set up so that we could actually send something from the software. Okay, a lot to do. Let's get started. Okay, so a good place to start learning about RS-232, like so many other things, is Wikipedia, of course. And they show this 25-pin connector for RS-232, but of course we're working with that 9-pin connector. And I didn't read through every line of this, right? But it doesn't mention that 9-pin connector anywhere. So there is this other one, DB9 Pinout.com. So we could see the specific pins of this communication protocol, and what they're mapped to, like which specific pin of that 9-pin connector, or D sub 9 or DB9 is pretty, yeah, DB9 look. So we're going to use 3 pins off of this. Pin 2 for receive, pin 3 for transmit, and then 5 for ground. You always need the steady ground. And so we're using this guy from McMaster, and it's not too bad, 2140. So this is a USB to serial adapter. It's actually going to have the little logic inside the head here to convert these the RS-232 signals coming in on this 9-pin connector to something that actually has an existing USB driver that Windows knows how to talk to. And then we're also going to use this level shifter. And this is twofold why we're going to use this. So if you notice, RS-232 standard actually lists some voltages that it runs at, which are +3 to +15 and -15 to -3, and that's huge. Our FPGA is working in the 3.3 to 0 volts range, and so this adapter is not going to source 15 volts. It's probably going to do the 5 volts that comes standard with USB ports. But if our FPGA is at 3.3, then it doesn't hurt to actually drop this down to 3.3. And also, it's a convenient little breakout. We only want the 3 pins, receive, transmit, and ground. And this has a 4-pin connector. You could see it right there. It has transmit, receive, and ground, and this fourth one, VCC. And that is actually how you tell it what voltage to shift the voltage levels to. And if we go over here to documents and schematic, you can see how everything's sort of connected. To the 9-pin out here, you have RS out connected to pin 2, which is, you know, what we expect. And you have RS in connected to pin 3. Again, that's transmit, or, you know, opposite of out. Pin 5 is ground. Again, pin 5, ground. Great. The only difference really here is we have this extra VCC. So, you know, we have this 4-pin connector on the right. Transmit, receive, ground. VCC is mostly used to turn on the LEDs on the board, and this little opto isolator to actually send the signals out to receive and transmit. So it's twofold. It's both it's a really convenient thing. It's not too expensive, 16 bucks. The voltage protection is just generally a good idea too. And I do have links to both of these on MadeByOzzy. In case you need to go reference this or get the links. Of course, all the links for all of these, the Wikipedia, all this, all that, is in the description below. Okay, so that's our physical setup, right? I should be able to plug this USB into my laptop. I'll plug this level shifter into this adapter's DB9 adapter. Now I have some pins to tie into my FPGA, right? So here's my handy dandy manual, the DE0CV manual. I'm going to look at the expansion headers, the general purpose IO expansion headers. They give me 40 of them. Oh, they're 40-pin headers. It's 36 pins that I have available to me. It shows the wiring. And what do I have here? I actually have, so I have a 5-volt signal that I could use, and I have a 3.3 volt signal that I could use. And then there's a ground provided right there as well, and then all the general purpose IO bits. So what I'm going to do is we're going to go ahead and connect up to this little quadrant right here. We're going to connect the VCC of that level shifter to 3.3 volts at pin 29, the ground to pin 30, and then we'll just use pins 31 and 32 for transmit and receive. 29 to 32. That's the plan. Cool. So immediately when I hook it up, I don't even need to configure the FPGA on, and I'll have this voltage available to me here and the ground, and that level shifter has some LEDs on there. So if I can send something from the PC to one of those pins, I should be able to see one of the LEDs turn on briefly if I have the voltage hooked up. But to send something from the PC, I want to write some Python. I'm going to write a little Python script, and I'm going to use this library here, PySerial. And it looks pretty easy, right? I'm going to import serial, and I'm going to, it's pretty easy to set up. Right here it's telling you some default parameters. 9600, 8, N, and 1. So what are these parameters? And if you go over here to MadeByOzzy, I have listed out sort of what they are and what I'm going to use for this demonstration. So the first one is actually baud rate, which is it's like bits per second. The only caveat is it does dictate it's bits per second, right? What that means is the clock rate here is, if the baud rate is 115.2 kilohertz, then this time step here is 115.2 kilohertz, but the actual data sent is not 8 kilohertz because you have this overhead of a start bit and a stop bit. So you always have this 2 out of 10 bits is 20% overhead. So they sort of just made up this term baud rate instead of bits per second. But anyway, PySerial, the default is 9600. We are going to set it to 115.200. This is the fastest that the standard supports, and that's what we're going to use. So we would have to use this command right here, showing how to change it to a different baud rate, 19200. Of course, we're going to use something different. That 8 is number of data bits. You can set this to 7, but you'll almost always see this at 8, and we're definitely going to use 8. N stands for no parity, which is pretty common. Parity is like an error check. It does a little or and or something on all the bits, and it needs to match. We're going to ignore that. And last one, 1, number of stop bits. And that just dictates how many time steps you wait. So by default, it's only 1. You could wait 2. We're only going to wait the 1. So yeah, it looks like some pretty easy Python code. Let's go set that up. Okay, so the first thing I'm going to do is I'm going to come here to the repo, the copper repo. I'm going to make a new folder for Python. Okay, now for Python scripts, I actually use PyCharm. So I'm just going to go ahead and create a new, and I'm going to create this in the folder I just made in the repo here, in the repo copper. All right, create. Okay, cool. Okay, so let's go ahead and make a new Python file. Let's name this test serial, I guess. Why not? Right? Yes. Remember, add everything to Git. There we go. Okay, so what's the first thing we do? Import serial. Okay, import serial. All right, and it's not installed yet, so because PyCharm uses virtual environments, so basically everything import and install per project. But this is something I wanted to point out to you guys. Look, by default, PyCharm gives you this. You could install the package serial. We don't want the package serial. That's very that threw me off the first time. We actually want the package PySerial. Serial is actually something for JSON decoding, which is totally different. And if you go to PySerial installation, you pip install PySerial. It's pretty unambiguous. So let's go here to File and then Settings, and then go down to Project Python, Project Interpreter, and from here we could go add any modules we want. So let's search for PySerial. Okay, there it is, and let's install package. Okay, install successfully. Cool. Okay. Good to go. And what's the next thing we need to do is now we need to create a serial object, and we have to give it this string, open serial port. So that string, what is that string? So what that's actually referring to is the name of the serial port on your computer, and that doesn't exist yet because I haven't plugged in the this adapter into my computer yet. So as soon as I plug this in, it should install some drivers on my Windows and then actually create something called a COM port, a serial COM port, which will have some name, and the name is usually like COM0 or COM1. So let me go plug that in right now and let's see what the name is going to be. Okay, so I got my device manager open here, and this we should see it change. So I'm gonna go ahead and plug that in right now. Okay, so Windows picked it up. It heard something. My device manager refreshed, and it looks like let's see, does it show up somewhere? Oh, ports, COM and LPT. Get rid of all the USB stuff. Prolific USB to Prolific is probably the company that makes this, makes a chip or whatever. USB to serial COM port, COM3. So ours is not, it's not COM0, not COM1, it's COM3. Okay, so instead of this, I'm just gonna go ahead and copy the rest of this. And let's go ahead and put it on our project here. All right. Obviously I don't need these because, I'm not printing to council. And instead of that, I'm going to put in COM3. This is going to write the binary string hello, and then it's going to close the port. So okay, let me just see if this actually runs. What happens on the Python end if this runs? Okay, prints that. Cool. Now I need to actually go connect this physically up to the FPGA to see if I get an LED blinking when I send this. And you know what this actually got me thinking is I'm pretty sure I must have connected this adapter to my computer before, because I'm surprised there was no driver installed or anything. So that's just FYI, Okay, so I have my FPGA here, and I have my level shifter here, and I don't think I could get it to focus on the words here, but the first one is VCC, and then ground, and then transmit, and then receive. So right now, first things first, I'm just going to hook up VCC and ground. So VCC here is the red wire, and ground is the black wire. And they all have these male connectors, but I got, male connectors on the FPGA. So I got this little female to female jumper cable. So I'm going to connect black to black to keep that consistent, and then white to red because, well, I don't really have my choice with the colors. Okay, and then, So 3.3 volts and ground were actually the 6th pin up from the bottom. So if I'm looking on the header and I count up and I go 1, 2, 3, 4, 5, 6, that's where I'm going to want to connect my ground and VCC. So on the left was VCC, which is the red, which is mapped to white. Again, not really my druthers, but okay, let's count. 1, 2, 3, 4, 5, 6. All right, and then ground is right next to it. Cool. Okay, so now I just plug in my adapter here. The other end, the other USB end is in my computer, and I'm going to plug that in. Okay, great, and turn on the FPGA. Okay, and my computer picked that up. Maybe you heard it. And no LEDs are on right now. Okay, so let's go see what happens if I send that little script from Python. Okay, so I'm going to go ahead and hit press run on Python script right now. And okay, there you go. You could see a little LED turn on right now. Okay, so let's see if I could run this one more time, and you see it turn on again. All right, cool. Success. We know we are successfully sending some characters from our software side. Okay, so next steps, I need to actually add some general purpose I/O pins to the configuration. So I need to go into the QSF file and add these pins, K19 for pin 31 and P18. Okay, so let's go here to the repo. Okay, and then here in FPGA, and here's copper.qsf. I'm going to edit it with Notepad++. That's what I've been using to edit this here. Okay, and then just to the bottom of the local assignment here, and let's make 2 new ones. Set location assignment pin, what was it? K19. And we're actually going to set the left side. Let's just set this to okay, I'm actually going to break the naming convention. No more GPIO 0 D26. I'm just going to name this RS-232 TX. Okay, and then accordingly, I'm going to name the other one RX, whichever one that is, P18. Okay, P18. RS-232 RX. Okay, cool. Save. Nice. All right. I like closing it. Great. Okay, now let's open up the Cordis project file. And the BDF. Cool. Okay, so we want to make sure that our pins are actually working and they're mapped correctly and that we can actually see LEDs blinking on our little level shifter tool. So let's make a little verilog test module, file new verilog HTL, to help us test what's going to happen here. So I'm just going to save this right now. Save it here in our library, and this is going to be RS-232 test module. Cool. Okay, so I'll just name it a module, RS-232 test module. Figure that out in a second. And module. Okay, cool. And I suppose what we're going to have is an input for receive and an output for transmit. Okay, and then what I want to do is I want to tie this receive bit to an LED. So I'm going to have an output, I'll call it RS LED out or RX LED out. So I'm basically just going to assign this input pin RX to RX LED out. And then this transmit, I want to have some way to control it. So I could tie one of the push buttons that I've set up before to actually turn that on. And the second thing, I want to have an LED to view that as well. So I'm going to do a transaction button in and transaction LED out. Okay, cool. Save. Okay, so let's actually define the inputs and outputs. Define IO. Okay, input is RX, and then also I guess transaction button in. Okay, and then output would be transmit, then RX LED out and transmit LED out. Okay, cool. Let's assign receive button to that LED. Assign, I'm sorry, the other way around. RX LED out equals RX. All right, that should do it. And then let's go ahead and assign that push button in to, I guess, all of these basically. Okay, assign TX. Okay, assign TX equals TX button in. Okay, assign TX LED out equals TX button in. Okay, cool, save. Let's try and build a symbol out of it. Quick way to see if this logic makes sense. Cool, symbol worked. Awesome. Okay, so I want to use it here in my file, and oh yeah, I forgot. I actually need to declare. I need to create new inputs and outputs for them. So here I'll create an input, and then I named it, I think, RS-232 TX. Oh geez. You know, was it capital or was it that's I really shouldn't have closed this, huh? Okay. Yeah, capital TX. That's really important. Can't go messing that up. Okay. Actually the input would be RX, obviously, not transmit. Okay. The output is transmit. Okay. So control, click and drag, RS-232 TX. That's the transmit. That's the output. That's the input. Okay, save. Okay, so let's go ahead and drop in the new symbol we just made. So double click, and here in project it should show up RS-232 test module. There it is. Okay, so let's go ahead and tie this receive here to I just typed it out. You think I'd remember the name? RS-232 RX. RS-232 underscore RX. And then, while it's fresh on my memory, RS-232 transact out. Okay, so transmit button in. We just need to pick a button. So what inputs do we have? We have key 0, key 1. We're using a few of these, right? Which ones are we using? There's key 0. It's tied to that. Are we using key 1 for anything? I don't think so. All right, cool. Let's key 1. Key 1 is going to be the button. That's going to be the second button. Key 1. And if you're wondering where all these came from, you could always go check out the previous videos where we actually configured the I/O for this specific FPGA development kit. Okay, we need to pick a couple LEDs out. So we've used all the way. So there's 2, 3, 4. So I guess I could start on 5. LEDR5, and then the other one could be LEDR6. Cool. Save. Okay, and let's see if this compiles. There we go. Okay, compilation was successful. But you know what? I immediately see something is wrong. So the ALMs used here is 75, and the total registers here is used 137. And let's see, is that even possible? So what I did is I defined a couple inputs and outputs. I would have expected this number to go up because I just added some logic to it here. But I guess looking at it now, well, let's see. Okay, let's actually write this out. Tools, programmer. And let's write this out. Okay, let's go check it out. Okay, so check it out. The LEDs are actually on right now. So that means something's happening. What happens if we press our test button that we did in the verilog? Okay, so the LED does turn off. Okay, cool. So the ALMs and registers can stay the same, and logic is still implemented. Okay, so that's cool. I just learned something. Okay, but it's really interesting to note too that the LEDs are on right now, but nothing's actually happening. I mean, logically, they shouldn't be on right now. So I'm thinking this level shifter just inverts it. So let me try sending from the Python script and see what happens. So let's watch our LEDs. Okay. You know, it's too tough to tell. I can't tell if either of them is turning off or on. I still see the LED turning on our little level shifter here, but I don't see something happening on there. So let's go see what's going on. First things first, I'm gonna actually get rid of those other LEDs. There's no reason to have these here anymore. They were a demo from a previous video. You could go check out that previous video if you want, but they're just getting in the way for us right now. And the first thing I want to troubleshoot actually is I want to see if maybe this just isn't turning on at the speed I expected, or maybe that LED actually is turning on and off, but we can't catch it because it's doing it too quickly. So we're gonna build a latch. Okay, so let's go make a new verilog module. Okay, verilog HDL file. Okay, we're gonna name this one module general latch. Okay, and it's gonna have the clock and reset inputs. We need those. And then it's going to have an input. Well, I can't call it input, right? It's going to have a signal in and a latched out. Okay. And module. Okay. And save. Let's go ahead and name the not in output files and library and general latch. Okay, let's define the inputs and outputs. Define IO. Okay, input clock, reset, and signal in, and output latched out. And this is actually going to be a register because in order to latch anything, you need to preserve memory for some time. So let's get the normal synchronization stuff. Always at pause edge clock, begin, end. Always. Cool. Easy. Okay, and then the reset. If not reset, begin, end. Else, begin, end. Cool. And then all we're going to do here is assign latched out equals, equals 0. Okay. And then else, we're going to actually look for the status of signal in. So what I mean by latch is if signal in ever goes high, we are going to latch this latched out to high. And the only thing that could turn it back to 0 is this reset condition. That's it. Okay. So what we're going to do is latched. We're going to watch if signal in, begin, end. If signal in, then we're going to set this latched out to 1. Okay, that should do it. Save. Let's create a symbol for this. Create symbol copper.bdf. Yes, everything has been changed a little bit, right? I erased those LEDs earlier. Okay, symbol successful. Cool. Okay, so let's go ahead and drop this into our schematic file. And let's do it for both of our LEDs, but we're actually gonna have to do something. We got to invert them because how I set it up is to come on if signal in ever goes high, then latched out will remain high. But we see just from the LEDs, these are always high. So we actually need to invert them. So let's see. We go in here and let's look for the primitives, and I'm sure there's a not in here somewhere. Logic, not. Cool. Okay. And our signal in needs to go to that not. Move it down because I want to steal a clock and a reset from somewhere. Like right there. Control C. Control V. Drop it right here. Cool. And then, so I'm actually going to replace this. So instead of going to the LED directly from there, I'm going to run it through this latched signal. And then, wire this to right there. Okay. Alright, and I'm going to make a copy of this and do the same thing for that transmit out. Cool. That wire, man. Okay, I need to delete that one. Steal this one. Control X, Control V. Okay. No, I keep double clicking. You know, all these different IDEs have their own intelligent way of doing things, and you know, oh jeez, Cordis, come on, give me a break here. Throw me a bone. All right, save. Okay, let's see if this compiles. Oh, no compilation. Okay, let's see. Let's figure out why not. Okay, so what's the error here? Function of type general latch and instance inst is already defined as a signal name. And then again, another the same error is or type of not instance. Okay, so this is a copy paste error. This is something I thought Cordis was going to handle this for me. Apparently not. So recall when we hard coded in instances, we have to give them unique names. Apparently when I hit copy paste, it did not increment a name. So okay, so instead of instance 0, and then this one be instance 1, and then it looked like this same already exists. Oh, okay, I guess I need a instance 1 does not work. Instance 3. Okay, what about instance 36? Interesting. Okay, so look at that. That is very interesting. Apparently, it's very picky about the instance names. Maybe that has to do with these. I can't even repeat that. That's very interesting. Instance, I don't know, 42 and instance 43. Huh. Okay, good to know. Save. Now let's see if it compiles. Cool. Compilation successful. Let's write this out. Okay. Open up a programmer and write. Awesome. Let's go check it out. Okay. All right. Much cleaner. All the LEDs are off. Okay. So the one thing we didn't know is this switch was controlling the LED is supposed to out here. So I added that latch. If I press it, okay, LED comes on. Great. Now, what about if I run the Python script so I can actually send something out? Will the other LED turn on? And I just ran it, and you know what? Nope. Okay, so I see the LED turn on the level shifter, but not on our FPGA. Okay, some more debugging to do. If you're viewing at home, you may have noticed this is actually a really silly mistake on my part. Well, apparently, if you want to read a hardware signal, you actually have to plug the damn thing in. Okay, so let's go ahead and do that right now. So that's transmit is the green one, and receive here is the yellow one. And again, I have male connectors, male pins when I need male to male, so I have this little female to female. So I have yellow and green. I'm going to map to yellow and orange. You know, I guess we just don't get our choice of colors whenever we want, but that's okay. It's only 4 colors. We could remember that, right? We're intelligent fellows. Okay, so I have transmit here mapped to green, which is mapped to orange. Okay. And transmit was actually mapped to pin K19 on the FPGA, which is just below VCC, just below that white one. Except I'm not going to plug in transmit to transmit. I'm going to plug in transmit from here to receive over there. Because that makes sense, right? This is transmitting to the receiver over there. So that means I need to plug in the transmit that I have here, which is green mapped to orange, over to pin P18, which is on the right side just below the ground reference here. And there we go. And then I know where the other one is, so I know it's right next to it. Okay, bear with me. All right, now let's try this out. Okay, I'm gonna hit reset on this. Okay, I'm gonna test my button there. Okay, and look, if you actually see it, when I press the button here, it does turn on a corresponding LED there. So we know we got some mapping, right? Now let's press the Python script. All right, Python script, and it latched. Great. I wonder if we could have done this without the latch, but now we know we at least have all our I/O mapped out and working, and great. Yeah, bear with me. Okay, guys, I am so sorry I just made you watch me build a latch for no reason and debug what was probably like the goofiest like beginner mistake to make. Bear with me, you know. This is just, you know, some fun. I was throwing together a video on Saturday night, and, you know, I was relaxing as adults will do. So you see the effects of, you know, trying to code and build projects when you do that. But we finally got it working. We have everything tested out. All our I/O is connected. We know we're receiving from the computer. We know we are transmitting from the FPGA. I mean, right now it's only with the button, right? But you know, we're gonna build some code so it's automated and actually doing something. So Now, on the next episode, we're actually going to try and build a whole verilog module to handle reading the 8 data bits that get sent over that receive pin. So remember, we have a start bit, 8 data bits, and then a stop period. So that's going to be, we're going to get our first exposure to what's called a state machine, a very important programming tool that we're going to use a lot. So, I really hope you guys will join me for that. If you like this video, or even if you don't like it, hit like, and then hit subscribe too, so you can keep, keep up to date as I release these videos. Really helps me out if you, hit subscribe and like. And if there's any questions at all, I very much welcome questions or comments or anything that you, were confused about, that I didn't cover correctly in the video. Just drop a comment down there. I will answer you. I assure you, I will answer you. Okay, thank you for joining me. I hope I see you guys next time. Have a good one. And here I want to remind you guys that you can always go to MadeByOzzy.com if you need to look up something like a link to that USB RS-232 adapter, or the level shifter, or the parameters that we're going to use, or if you link to the GitHub or the user's manual. And then, of course, if you want to support me in this way, there's cryptocurrencies that you could send me, and here are my receive addresses. Thanks for watching.